Word equations. Let's take a look here. All right, learning targets. Fun. Write chemical formulas. Yay, we get to do that again. Balance chemical equations. Review of last class. And identify correct state symbols. These are the things that you need to be able to do to write out word equations. All right, so we write chemical equations to represent the chemical reaction that takes place. Like before here, showing this reactants. Iron is solid metal. And we identify lots of our state symbols based off of how they exist at normal conditions. So anything on the periodic table that is, most of the stuff on there is solid at room temperature. Okay, like water is a liquid at room temperature. Those kind of things, like hydrogen is a gas at room temperature. And then the Fe2O3, that's actually rust or iron 3 oxide. So we know rust is a solid. I'm sure you're familiar with rust. But the word equation, how it would be written is like iron, metal, water react to yield or form hydrogen gas and iron 3 oxide rust. Okay? So keep that in mind when you're paying attention to identifying the state symbols. Think about how it would be at normal conditions. Most everything is on the periodic table is solid, but remember, bromine's a liquid, mercury's a liquid, and then you have your gases like hydrogen, nitrogen, oxygen, fluorine, chlorine, and then the noble gases. Those ones are, of course, gaseous at room temperature. All right, things that you need to remember. Formulas must be written correctly in order to balance. If you do not get the correct formula, obviously it's going to have a trouble trying to balance it. We need to review the naming systems for ionic, covalent, and acid in order to make sure that we are writing the chemical formulas correctly. So I put in the chart here. You guys also have this chart on Classroom, and you can use it at any time to help you. So remember, looking at the three naming systems over to the left here. My left, your right. Maybe it's your right. I don't know, your left. This side. Okay, we'll just go with that. This is going to be the ionic side. Okay. And what is the key to writing ionic compound formulas always? What is like the overall thing that you need to ensure to make sure you get the correct ratio? Does anybody remember? What do we need to do to make sure we get the correct ratio? What do we look at in order to ensure that? It's not really the coefficients, but what is specific about the ion that we need to look at? At least you're thinking numbers. It is a numerical value that we have to look at. The charge, yes, you have to look at balancing the charges. Remember, you have cations. What type of ion is a cation? What's the cation? What type is it? Those are the positive ones. That means they lose electrons, right? So they have positive charges. And they're typically going to be the metal or the ammonium here, okay? The metals or the ammonium are going to be your cations. And they're going to be left of the staircase, okay? Left of the staircase on the periodic table. Like for group 1, those alkali metals, what charge do they always go to? Anybody remember what charge they go to? How many valence electrons does group 1 have? They have 1, so that means they're going to lose that one, so they're going to have +1 charge. Exactly right. Very good. Like group 2 goes to +2. We're going to review the charges of all the columns in a slide or two here, but I just wanted to get you thinking about this. Now, how do we identify the MOMs in word equation, like in written form, in words? What will you see if it's a MOM, a multiple oxidation metal? What will be present? Roman numerals, very good. And remember, the Roman numeral identifies the charge for you. So if it has a Roman numeral 3, that means it's a plus 3. If it has a Roman numeral 4, that'll be a plus 4. Okay? Very good. Now, the second element is going to be in the second half of the compound there. This one right here, second element. These are going to be your anions, okay? And what kind of charge do the anions have? They are negatively charged. Good. So remember, you're balancing out the charges to make them add up to 0 in order to get your compound. So that would be the how to do the ionic, writing the formulas, getting the correct ratio there. Covalence, easier. What system does the covalent one fall under? What do we use there to identify our subscripts? How many of each atom are in there? We use the prefixes, and that's mono, di, tri, tetra, penta. The regular prefixes, not the organic prefixes. That's meth, eth, prop, and bute. Different prefixes there, but we use mono, di, tri, tetra, penta, and so forth. Okay, and they're always nonmetal, or nonmetal metalloid. They can have that combination too. And then for the last but not least, over here with the acids. Okay, acids. What should always be in the front of the compound to determine it's an acid? We always have hydrogen first. Now, two types to look at here. We have the monatomic ones without oxygen. Okay, those are like the ones that are off the periodic table. That's when you do the hydro something ic acid. The polyatomics have with oxygen, these guys. You want to have your polyatomic ion list out too, because you need to reference those for both ionic and acid naming. So we have two options. If it's an ate ending, I ate something icky, it's just something ic acid. And if it ends in ite, it's got the OUS ending, like Sprite is delicious. Okay, so you would change the ite to OUS. And what is the charge on hydrogen always that we're going to use in order to write the correct combination here? Hydrogen always is a, in an acid, hydrogen always has what charge? How many valence electrons does hydrogen have? Where is hydrogen positioned on the periodic table? Very good. It's above group 1. Remember, it's not a metal, but it's above group 1 because it has 1 valence electron. So what charge is it going to form when it forms an acid? Plus 1. Very good. It's always going to be H plus with the anion. So you write your ratio based off of that. It's always H plus, and then you determine how many hydrogens you need based off of the charge of the anion. All right, so here's basic gist of the periodic table. You have the alkali metals that are, this is group 1, alkaline earth metals plus 2, group 2. The first set of the transition metals are usually plus 3, but you don't have to know that. This is what? Boron, aluminum, those ones plus 3. Now, this is plus or minus 4 here, but most of the elements in group 14 do covalent bonding. Remember, your group 15 are minus 3, minus 2, minus 1. So group 15 has 5 valence electrons. Remember, it gains 3 rather than trying to lose 5. 16 gains 2 to the 6 that it already has instead of losing 6. And then the halogens have 7, so they're going to gain 1. Okay? So keep that in mind. And yes, you have these 3 that are not moms. Not moms. Silver, zinc, cadmium. We just have to know those charges. They do not get Roman numerals. They're not up here, but I'll put them up here. Remember, tin. Tin's right here. Tin and lead. Does anybody remember what charges these guys go to? Because they are moms. Anybody remember tin and lead? I know, so quickly it leaves us when we don't use it. Yes, it's +2 or +4. Very good. So those ones get Roman numerals. They'll be written in the equation anyways. You'll see that. All right. Once again, I put this in the slides, but you have the sheet in classroom. Definitely, if you have it already out or don't have it out, get it out, because you'll need to reference your polyatomic ions as well to look up their formula, which is also not just this part, but you also need to have the charge there so that you can write the correct ratio. So have this out. Be able to look up any of the polyatomics because we use them to write the correct formula. One other little added bit that people forget is those diatomic elements, the twin molecules. If you don't write them incorrectly, it will not balance. Like if you just put Br instead of Br2, it's not going to balance right. Don't forget your Brinkelhoff. Remember, it's also the 7 rule. Start at 7, make a 7. Don't forget hydrogen's the 7th over here. These guys always have to be written with the 2, or it's not going to work. So, bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. So definitely don't forget your diatomics. They're important. So 7 rule or Brinkelhoff, however you need to remember it, that's what you want to do. So example here, you wouldn't just put H plus O gives you H2O. No, it would be H2 plus O2 gives you H2O. Diatomics. All right, that brings us to our practice now. So here, we're going to start with some basic ones. We're going to do some more complicated ones, and then you can do the ones that are in the choice board. All right. Something to also note about state symbols. On the periodic table, we briefly touched on it, I think, back in Unit 3. Most of your regular elements are going to be solids at room temperature. And we're talking about the physical states at normal conditions, which would be room temperature, and about 1 atmosphere for the pressure. Metals, besides mercury, because mercury is a liquid at room temperature, all the other metals you would identify as a solid. The other liquid is bromine. Bromine and mercury, but bromine's a non-metal, mercury is a metal. Those two are the ones that exist as liquids at room temperature. And then you have your series of gases like hydrogen, oxygen, nitrogen, fluorine, chlorine, and the noble gases. Those ones are gases, of course, at room temperature. So those are a couple little things. When you think of the substance, how does it exist at our normal conditions? And that's how you try to address the state symbol. So here, because we're going to start out with our zinc metal. What state symbol should I put next to the zinc metal? Zinc's not diatomic, so I don't have to write a 2. But when you think of zinc or iron or nickel or copper, what do you normally think of its physical state being at? A solid. Good. So we put an S here. Now for the next reactants. Okay, so that's the zinc metal. Lead to nitrate solution. So let's start here. Lead. The lead 2 part. What does that tell me about the charge on the lead? So it's going to be a what? A 2 plus. Good. Now, who knows what the formula in charge of nitrate is? Nitrate's obviously one of those polyatomics because it ends in ATE. So we need to be able to look those up and find them. What's nitrate? Close. You're close. It's NO something. NO what? How many oxygens on the nitrate? NO3. Very good. What's the charge of nitrate? -1. Very good. -1. Now that we know both the cation and the anion, we can figure out our formula. Now remember, the charges have to add up to 0. So lead has a +2, the nitrate has a -1. How many of each do we need in our formula? How many leads, how many nitrates do we combine to make lead to nitrate so that the charges will add up to 0? Yes, we need 1 lead because that's +2, and then we need 2 nitrates, so we get -2, right? So here we do Pb, and when we have a polyatomic that we need another group, what do we use around it? Parentheses, exactly right. So we do parentheses, put the NO3 in the middle, and then stick the 2 outside, like so. Now for the state, it says solution. When it says solution, what should we automatically think of? Mixture with what? What does it mix with if it's in solution? It's mixed with water. Very good. So if it's in solution and mixed with water, what do we call that in terms of our state symbols? Anybody remember? It's not a liquid because a liquid would be a pure substance. Solutions are actually a mixture of something and water. Something being dissolved in water. There you go. AQ. Exactly right. Aqueous. So that's AQ. Now we're going to go on to the products. First one is zinc nitrate. So we have Zn, we already know nitrate, right? Because we already figured that one out. What's the charge on zinc? Zinc's one of those ones that's in the transition section that only has one oxidation state, like silver and cadmium. +2. So this one's a +2. Very good. So how would we write the formula there? How many zincs, how many nitrates? Zinc's +2, nitrates -1. So we need 1 zinc and 2 nitrates. So put the parentheses, add the 2 on the outside. Now it also says solution here. So that means this one is going to be AQ as well. I'm just running out of space here, so I put it down below. Our last substance, solid lead. So all we have to do is add that in. That's pretty easy. Lead's not one of the diatomics. And there you go. So we've wrote out our formulas. We put in our state symbols. Now all we have to do is balance. So take a look there. Are we good? Should go ahead, if you need to, you can do the little chart thingy. We have zinc, we have lead, we have nitrate on both sides. So 1 zinc, 1 lead, 2 nitrates. 1 zinc, 2 nitrates, 1 lead. Oh, look at that. It's already balanced. So we don't have to do anything there. That's nice. You could use the chart if you need to. You don't have to use the chart, but you can if you want to. All right, let's look at the next one. Everybody good with this one? All right. Chlorine gas reacts with a solution of potassium bromide to produce a solution of potassium chloride and liquid bromine. So, what do I write for my first reactant, which happens to be chlorine gas? What's the first question I should ask myself when anything is just an element by itself? Is it what? Well, it says it's a gas, so I know that part. But what should I ask myself about the element itself? Is it diatomic? Is chlorine one of the diatomics? Is it part of Brinkelhoff or the 7 rule? Yes, it is. So this one has to be Cl2. You don't put it as Cl2, it's wrong. And yes, it is a gas, so I'm going to put that in there. G. It tells me, yay, that's easy. Now it's reacting with a solution of potassium bromide. Potassium is K on the periodic table. Bromine, of course, is Br. Potassium happens to be a metal. Bromine happens to be a nonmetal. What type of compound are those two elements going to form? Ionic. Very good. So we need to locate and figure out their charges. What is potassium's charge? What group is potassium in? It is in group 1. Very good. So that means its charge is going to be +1. The alkali metals are all +1s, right? They have 1 valence electron, they lose 1 valence electron. Now for bromine, what group is bromine in? Because it's now acting as the anion. Which group is bromine in? It is in group 7 or 17 or 7A or 17. Yes. So what would that charge be? -1. The halogens, they all have -1. Remember, because they gain 1 electron. Because they have 7 to start with to get their octet. Now, it's +1, -1, so we just need 1 of each. So that's pretty easy. It says it's in solution, so what am I going to put next to the state symbols there? AQ, very good. AQ. Now let's go on here over to our products. Producing a solution of potassium chloride, so that's K plus with Cl. What is the charge on the chlorine in that compound with potassium? What group is chlorine in? -1 again, because it's a halogen too. It's right above bromine. So yes, that one's a pretty easy one too, because it's +1, -1. It's 1 of each. Add up to 0. And this says solution as well, so we're going to go with AQ. Now for the last part, bromine liquid. What do we got going on there? How do we write that? Bromine by itself is just an element, but we should always ask ourselves, is bromine one of those diatomics? Start at 7, make a 7. Don't forget hydrogen's a 7. Who's number 7? Nitrogen 7. Make a 7.
Yes, it is.
It is a diatomic. Very good. Yes. So we were going to write Br2. And yes, it says liquid, so we can just put the L there. Very good. Now, just by scanning it over, does this one look balanced?
No.
Sure? Which ones are out of balance? I see
Yeah.
2.
Chlorine and bromine.
Bromine and chlorine are out of balance. Very good. So we needed balance. You don't have to do the chart if you don't need to, but some of us, we need a visual aid, so I'm going to do the chart for me. So, over here I have 2. Here I have 1. Here I have 1. On this side, 1 for the K, 1 for the Cl, 2 for the bromine. Which one you want to start with? Chlorine or bromine? Chlorine, 2. Okay, so we have 2 over on the reactant side right here. So that means, what do I put here to fix that? Good, put a 2 here. So that's going to be 2 here and 2 here. Hey, this is nice. It's going to work itself out, right? Because I need 2 of the K and 2 of the Br, and guess what? They're together. So what do I put there? I just put a 2, and we're done. Everybody good? All right. Very, very good. Oh, by the way, real quick, just to quiz ourselves, what type of reaction is this? Did we identify the type? What type do we got going on here? Yes, it is a single replacement. It's one of the anion switches. We have bromine switching with chlorine. So this is a single replacement for those that are interested. All right, let's look at this one. I think we can tell the type of reaction this one is because it says barium iodide solid decomposes into barium metal and iodine solid. Yay! So this one's obviously decomposition. So that means we only have the one reactant. We have to figure out how to write it though. We have barium, we have iodine. Barium's a metal, iodine's a nonmetal, so this is an ionic compound. Let's go to the periodic table. Let's figure out some charges here. What is the charge on barium?
Barium is +2.
It is +2. Very good. Because barium is an alkaline earth metal. It's in group 2. Iodine, what's its charge?
Oh, it's negative.
It is -1 because it's a halogen. And yes, you're right. If it was by itself, it would be a diatomic. All right, so it's this -1. Very good. Very, very good. Okay, so now how many of each do we need to make this formula work? So BaI2, good. 2 of the iodine, 1 of the barium, and this is a solid. It's going to decompose now into barium metal. So Ba, now ask yourself, Ba, is that one of the diatomics? Is it one of the diatomics? No, it's not. Okay, that's a no. So we're just going to put an S there because it's metal, solid. And what about I? Iodine solid here, so this is yes. We would put a 2 here and an S there. Now, let's look for balancing. What say you? Is anything out of balance?
No.
That one good.
That one's good, right? 1 barium on both sides, 2 iodines on both sides. This one is already balanced. Very good. Don't have to do anything to it. Excellent. Now for a more challenging one. Now we got some acid in there. Calcium hydroxide, that's base. All right, let's look here. Phosphoric acid, this is the first reactant. All right, it says acid, so I know I'm dealing with an H plus to start with. But now I have to figure out my anion, my polyatomic anion at that. Because it's not hydro something ick, it is just ick. So, because of this ick ending, are we dealing with phosphate or phosphite? Which one is it? 8. Very good. We are dealing with the 8. Now all we have to do is look it up and figure out. It's going to be PO something. What is the rest of the formula? What is phosphate? PO4 what? Oh, I gave you the 4. Okay, what's the charge? It's PO4 minus 3. Very good. Thank you. So, now to write the formula. How many of each do we need to write our formula? We want it to add up to 0.
3.
Oh, yes. Sorry, wrong. H3, we need 3 of the hydrogen and 1 of the phosphate, PO4. Exactly right. So this is phosphoric acid. Now, what physical state is acids always in? Since the definition of an acid is to produce hydrogen ions in water, what kind of physical state are we looking at here? You've got the hydrogen ions and the water. It's a mixture. It's a solution. So acids are always going to be designated as what type? Not liquid, it's AQ. Yes, exactly right. Always AQ because it's a certain amount of hydrogen ions in water. Now, if it's highly concentrated, you have more acid in the water. If it's not as concentrated, so, say you're talking about your soda, which is about a pH of like 4. Not as concentrated as stomach acid, which happens to be at like a pH of 1. But they are both mixed in watery solution, so they are aqueous. Next part, calcium hydroxide solution. Here's calcium. What is the charge on calcium?
Calcium is +2.
It is +2. Good. It's an alkaline earth metal. Now we have to figure out what hydroxide is. It's one of those polyatomic ions. Correct. OH negative. So, how do we write that formula? How many of each do we need? 2 hydroxides, 1 calcium. So don't forget your parentheses. You need to keep the group together. Stick the 2 outside. Now it tells you this is solution. So we know this is AQ. I'm going to put it down here because I'm running out of room. First product, calcium phosphate. We know calcium, 2+. We know phosphate, PO4 minus 3. So how many of each do we need to make that one work? Well, we have a plus 2 and a minus 3. So here we need a least common multiple idea. So what's the least common multiple between 2 and 3? Yes, because we got to do the plus 6 minus 6. So we're going to need how many calciums? We're going to need 3. That means we're going to need 2 of the phosphates. Exactly right. Now, figuring out the physical state here. What? It says it precipitates. What does that mean? That's a key word to tell you something about the physical state. What?
Oh, wait, no.
It's when you put the two solutions together and you see like the powdery stuff fall to the bottom. It precipitates out. What's that powdery crystalline stuff? If it's powdery, what phase of matter is it in? It's a solid. Precipitation results in giving you a solid. All right, so there's that one. And then our last thing, which is pretty easy, is water. And water at room temperature is always a liquid. Now we need to balance this one. This is definitely not balanced, you're right. But we recognize this as a neutralization reaction, right? Because you have an acid plus a base giving you salt and water, right? And I gave you a hint of how to balance neutralization equations. Does anybody remember what the hint is? What's the easiest way to go about this? What do we do to the water?
Don't you plus,
You make it HOH, exactly. We're going to change this to HOH. So it's like an H group and an OH group. So we balance H with H, and we balance OH with OH. Makes it a whole lot easier. So let's set up our table. This one I definitely need a table for. Gonna have to do that. So hydrogen, there's 3. Phosphate, I've got 1 on that side. Calcium, got 1. Hydroxide, I've got 2. Over here, calcium's at a 3. Phosphates at a 2. 1 hydrogen and 1 hydroxide. Definitely not in balance. Doesn't look like anything's equal. Now I would also tell you you should probably look at balancing the calcium and the phosphates first, because the HOH will probably work itself out. So we can start right here with the phosphates. What do we need to put here to fix the phosphates? Yes, we need to put a 2 here. Good. 2 times this 3 gives me 6. And 2 times the phosphates gives me 2 there. Now, what do we need to put here to fix our calciums? Correct. We do need to put a 3 here. So we're going to do that. That goes to 3. This goes to 6. Alrighty. So, as you can see, it nicely worked itself out for us, because what do we just need to put over here to fix it?
6.
Just need to put a 6 here. Very good. So that goes to 6, that goes to 6, and everything appears to be balanced now. Very good. Very, very good. So for our last fun example here, ethanol. Ethanol has that OH group. It's an alcohol. and it undergoes a combustion reaction. So ethanol is our reactant over here, like so. Now, when you hear about ethanol, that stuff that has the ethanol in it, like gasoline or beer or wine or something like that, what is its normal physical state going to be? A what? It is a liquid. Very good. If you think about the class of alcohols, whether we're talking about ethanol or propanol, propanol is what's actually in rubbing alcohol, like the stuff used to clean cuts and stuff. They are going to be in liquid at normal conditions. So the class of alcohols really doesn't matter which one you're talking about, whether it's methanol, octanol, pentanol, whatever, they're going to be liquids. Now, this is the other hard part. This is a combustion reaction, so we always have a certain reactant when it's combustion. What's the other reactant here? What will cause it to burn? What do you need to get a fire, flame, explosion going? What's the other component? For combustion, always need this reactant. What's that reactant? Yes, it is O2, oxygen. Oxygen is one of those diatomics, and oxygen is like 19% of our air, so it's in constant supply for combustion reactions. Now, what are the products of the combustion reaction? They're always the same too. So we have two of them. What's always the products of combustion? CO2 and H2O. Now, I'm sure pretty much most of you can know that carbon dioxide is a gas at normal conditions. But the resulting water from a combustion, most of the time, it's going to be in a certain phase because you have lots of fire and heat. So, what phase do you think it's going to be in? Is it going to be liquid water, or is it going to be water vapor or steam? Yes, because this is going to produce a lot of heat, so it's most likely going to definitely be a gas being given off. All right, so we set this one up. Now we're ready to balance. What's the method here for the balancing? No, we keep the HO together here, but you're right. We're going to do the CHO or the CHO. Go in order of carbon, then hydrogen, then oxygen. Balance carbon first, then balance hydrogen, then balance oxygen. So let's go ahead and add things up. We got a 2 here. 5 plus 1, that's 6. 1 oxygen here, 2 here, that's 3. So add it up. Over here on the other side. 1 carbon, 2 hydrogens, 2 plus the 1, 3 oxygens. So, starting with the carbon. What do we put here to balance our carbons? Put a 2 here. That's great. What do we put here to balance our hydrogens? We need it to be 6 total, so something times 2 gives me 6. So we're going to put a 3 here. Good. So that's 6. Now you add up your oxygens on the product side. So we have 2 times the 2, that's 4, plus 3 times the 1 is 3. This is a total of 7. Now, normally odd ones cause a problem. But if you look over here on the reactant side, in the alcohol, we have this odd one, right? So we have one here, but what can we put here to get the rest of it? Exactly right, we can put a 3 here, because 3 times 2 gives me 6, plus the 1 in the alcohol. Guess what? That also equals 7. So balancing the alcohols are slightly different than normal hydrocarbons. Does that make sense? Everybody good? Because those are the basic examples of word equations.